Have you ever looked at a massive storm or a star-filled sky and just wondered, how does all of that work? Well, today we're going to do just that. We're going to crack open the physicist's toolbox and learn the secret language the universe is written in. And don't worry, this isn't going to be some scary lecture. This is all about how we can use this language to find some really cool answers. Because that's really where it all begins, isn't it? With a question. You see, physics isn't just a bunch of dusty formulas in a textbook. It's about having this deep-down curiosity to look at the world around you and just ask, why?
So let's get right into it with a really high-stakes example. Imagine you see this monster forming on the horizon. It's incredibly powerful, it looks totally chaotic, and you know it's moving. Right now, the single most important question you could possibly ask is, where is it going? And this is no joke, right? I mean, people's lives literally depend on getting that answer right. So today, we're going to figure out exactly how physics helps us solve that mystery.
And you know, this way of thinking, this whole process, it's not just for tracking storms. It's how we tackle all sorts of massive questions. Like, how does a satellite just hang out in orbit without plummeting back to Earth? Or, why is the sky blue? And how in the world do radio waves carry our favorite songs through totally empty space? Yep, physics is the key. Okay, so if physics is all about asking these big questions, how does it actually find the answers? Well, you can think of it like the ultimate detective work. It's a method, a process, for decoding the clues the universe leaves for us, all around us.
And the case this detective is working on? It's absolutely staggering. The goal, believe it or not, is to uncover the fundamental rules that govern everything. We're talking from the tiniest subatomic particles to the biggest galaxies in the cosmos. It's really a quest to understand the actual blueprint of reality itself.
But, you know, every good detective needs a toolkit, right? You can't just walk onto a crime scene and solve the mystery without the right instruments and a set of rules. So let's take a look at what a physicist has in their kit. And here it is, the first and maybe the most important tool in that kit. How do you even begin to analyze something as incredibly complex as a tornado? The answer is, you don't, not directly anyway. First, you have to simplify. You create what's called an idealized model by basically stripping away all the distracting details, like the flying debris or its exact swirling shape, so you can focus only on the core things that matter, like its motion.
So once you've got that simplified model, you need a language to actually describe it. And the core words in this language are called physical quantities. Now that sounds fancy, but all it really means is a property of something that you can measure. You know, its length, its mass, its speed. They're basically the nouns in the language of physics. But here is the thing. A number all by itself is totally meaningless. If I tell you a car is moving at 15, what does that even mean? 15 miles per hour? 15 feet per second? You have no idea. That's where units come in. They give us the context, kind of like the grammar of this language, that lets us all communicate clearly. 15 kilometers per hour? Now we're speaking the language of physics. Now, this is where it gets really interesting, because sometimes a single number and its unit are actually all you need to tell the whole story. In physics, we have a special name for this, a scalar. It's any quantity that is completely, totally described by its magnitude, which is just a fancy word for a number. A scalar just answers the simple question, how much?
Just think about temperature for a second. If I say it's 20 degrees Celsius outside, you know everything you need to know. You don't ask, 20 degrees in which direction? Of course not. The number itself gives you the complete picture. And that, my friends, is a scalar.
Okay, but let's go back to our tornado. If we say its speed is 50 kilometers per hour, is that really enough information? Well, as we're about to see, when it comes to things that move, a number by itself can be dangerously incomplete. And that brings us to the other essential piece of our physics vocabulary, the vector. A vector needs two pieces of information to make sense. It needs its magnitude, just like a scalar, but, and this is the crucial part, it also needs a direction. So it answers how much and which way. So let's see this difference in action. Speed is a scalar. The car is going 100 kilometers per hour. See, it just tells you how much. But velocity, that's a vector. The car is going 100 kilometers per hour north. It tells you how much and which way. It's the same with something like force. Anytime you push or pull something, it's always in a certain direction, so it has to be a vector. And believe me, this distinction is everything in physics. It's how you can launch a rocket to a precise spot in orbit, or even program how a character moves in a video game. All right, so with this new idea, this difference between scalars and vectors, let's go all the way back to our original problem. We started with this chaotic, terrifying storm, and we were wondering how we could ever predict its path. Well, guess what? We now have the key.
And here is the big payoff. If a meteorologist gets on TV and only tells you the tornado's speed, 15 kilometers per hour, that's a scalar. And yeah, it's information, but it doesn't actually tell you if you need to run for cover. But if they give you its velocity, 15 kilometers per hour at 35 degrees north of east, that is a vector. And that right there is actionable intelligence. Now you know exactly which way it's headed.
And that is the whole point, really. That little extra piece of information, the direction, it isn't just some trivial detail for a science quiz. Out here, in the real world, it's often the most important part of the puzzle. It is literally the difference between knowing a threat exists and knowing how to get to safety. So, there you have it. From scalars to vectors, we've just seen how physics gives us this incredibly powerful toolkit for making sense of the world. It's a method for turning what looks like total chaos into something clear and predictable. So the only question left is, now that you have these tools, what mystery would you solve first?